So now that we have discussed how to implement the very specific circuit that behaves like a modular exponentiation function for the numbers for the base c equal to 13 and modulus 15. Next thing we'll do is we are going to program it using Qiskit. So what you can see here is just see. Hold on. Yeah. So what you can see here is a code in Qiskit. So these are the usual import statements, and this is the code. So in here, if you take a look at this, we have we define 4 input registers, quantum register, and then 4 output quantum register, and then we have classical registers which we need in order to hold the result of the quantum computation. And here we create the quantum circuit, passing the input register and the output register. So we just put some barrier here in order to make the code more, in order to make the diagram much clearer. And then we have this one here. We then create a X0 on the first output register, and then we create all of these control nuts. So from 0 input register, this is 0, and this is 0, 1, 2. The output register index 2. Okay, so if you do all of that, and here, this is also important. This is the control not gate. So here we have a control not on input register 0 and 1, and the output register is 3, and so on. Okay, so if we execute this, we will get a drawing. Okay, let's take a look at the drawing. Open image in new tab, and this is what you'll see. Okay, so similar to this one here. Okay, so that's the output. Okay, so the next thing is we are now going to implement the quantum Fourier transform. So for the quantum Fourier transform, we are going to implement this one here. So let me just increase the font size. Okay. So if you remember, this is the one which we have derived in the lecture series number 6, session 6. So it operates on 4 qubits, and this is the series of transformations of the Fourier transform. Now the H here stands for the Hadamard. So H0 means it applies on the qubit it applies to the qubit 0, and the V here, the Vij here, is the controlled phase rotation, and is defined by this function here. So Vij, or by this equation, Vij applied on this qubits with index xn minus 1 up to 0. Okay, so the control qubit here is I, and the target qubit is J. Okay, so this is the effect of Vij. So okay, so this is now the code to implement this series of operations here. Okay, so we define first the input register and define the output register, and then the classical register. Okay, and then create a quantum circuit composed of the input register and the classical register. And here, this is where you, okay, first we have the first Hadamard acting on the 0th qubit, okay? And then we have the control. After the Hadamard, we have the control phase rotation from 0 qubit to 1 qubit, okay? Okay, so we have here pi over 2, okay? So pi over 2, according to the definition, we have this one here is 2 to the 1, okay? 2 to the 1, because I minus j, okay, 0 minus 1 or 1 minus 0, the absolute value is equal to 1. So this one here is 2 to the 1. So we have pi over 2, okay? And then when the difference between the difference between 0 and 2 is 2, so this becomes 2 to the 4. Okay, so this one here, sorry, 2 to the 2. Okay, and the difference here is 3 minus 0, so this becomes 2 to the 3, so just like this formula here. Okay, so you do that. Okay, so you do that for all. Okay, so we only covered from here to here. Okay, and then you do another Hadamard. Okay, Hadamard on input register 1 until you do all of this. If you do all of this, then you will, this is the code. Okay, so let's run this. Okay, so this is the diagram. Let's open this in another tab. And here you can see the quantum Fourier transform for 4 qubits. Okay. Next is we now combine the circuit for the modular exponentiation with the circuit for the quantum Fourier transform, and this is what we get. Okay, so it's a more or less a copy paste. Okay, so let's run this and take a look at the circuit. Okay, so let's take a look. Open this in a new tab. Okay, so let's so first we have the Hadamard for all the for the input qubits. Okay, so that we'll have a superposition of all states in the input qubit, and then we apply the modular exponentiation, which is this part here. Okay, so this part is the modular exponentiation, and then after that After that, we do this, which is we apply the quantum Fourier transform. Okay, so after the modular exponentiation, we first measure the output register, and when we measure the output register, it will then collapse the input register, and the input register is the one which we apply the quantum Fourier transform, and then we measure. After that, we measure. Okay, so when we run this, okay, we'll just use a simulator. Okay, so we run this with 1,000 shots, and we plot the histogram. This is what we'll get. Okay, so take a look. Okay, so as you can see, every combination here has a probability of occurring. Okay, so let me open this one. Every combination here is a probability of occurring. So what we'll do is we are going to take a look at the combination with the highest probability, and then that's the one that we are going to, that will be our value of y. Okay, and once we get the value of y, we can then compute for the period. Okay, so in order to make this more programmatic, what we'll do is we use this Python code. Okay, so we use this Python code that will so as you can see, the output of the simulation is this this data here. Okay, so which is, we have the key, which is the binary representation of the number, and the number of occurrences. So here you can see that this one has 62 occurrences. Okay, which is this is 0. Okay, and yeah. So first, how do we interpret this this number? Okay, so to interpret this number, this is how you decode it. Okay, so the first, so the you can divide this into 4, and the rightmost 4 numbers, sorry, the rightmost 4 numbers represent the input qubits or input register, and then the output register is the leftmost. Okay, now if you remember, because of the design with Fourier transform, the order of the qubits are actually reversed. Okay, so for example, this is the output of the, when we measure the input register. So the actual value is the reverse of this. So if this is 1101, it should be 1011. Okay, so which corresponds to the number 11. Okay, so that's the that's how to interpret the output of the Fourier transform. Okay, so once we have this, what we'll do is use this Python script, which will sort the keys and output them in descending order. And then once we output them in, it will just output the keys. Okay, put them into a file. So let's run this. So the file is out.txt. Okay, so let's run that. Okay, this is what we get. This will then be written into a file called out.txt. Okay, and then we are going to use bash in order to sort it and get the first 10 entries. Okay, sort it in reverse numerical order using column number 5. Okay, so column number 5. So let's take a look again at the output. Column 1, column 2, column 3, column 5. So column 5 is the output. So we are going to, sorry, it's the count or the frequency. Okay, so we are going to sort this according to the highest to lowest, and then we are going to and the column second from the last is the number, is the value of y. Okay, whatever is the greatest, you are going to set that as a value of y. Okay, so what we'll do now is to run this, and then we'll see here that it's now sorted according to the highest frequency. Okay, so we have a 69 here, 62, and you can see that the value 0 is the highest, second with 15. But 0 will not give us any, will not really give us any information about the period. So we are going to use 15. So 15 is going to be our value of y. Okay. So once we have the value of y, what we can do is we now compute the period. Okay, so to compute the period, we are just going to use this formula here. Okay, so y over 2 to the n. So since we have 4 qubits, 2 to the n is 16, and y is 15. Okay, where did I get this y? Sorry, so I got this y from the output. This output. Okay. Okay, so using continued fraction expansion, you will then see that the continued fraction expansion determinated into this one here, and so if you get the partial sum, it's equal to 15 over 16. So which means that the period is 16. Okay, so how do we verify that's the period? So we have we just so this is our ciphertext, and what we do is raise this to the power 16 modulo 15. Okay, so 15 is our n in RSA. Okay, so now this happens to be equal to 1. Okay, so which means that it is the period. And then after that, we are then going to compute the inverse modulo. Okay, so what is the inverse of E modulo R? Okay, so inverse modulo with respect to R. So what we do is yeah, so E here is the value of E that we use is 3. So 3D prime is equal to S, some number S times 16 plus 1. Okay, so but this will be satisfied if S is equal to 5 and D prime is equal to 27. Okay, so if you put 27 here and here 5, then this will be satisfied. So which means that D prime is our inverse modulo. And then we can use it to decrypt the message M. Okay, so C to the D prime. So 13 to the 27 modulo 15. So M is equal to 7, which is our original message. Okay, so as you can see here, 8 also came up as the second highest. Okay, which we can also use that. Okay, turns out that we can use sorry, where is it? We can also use 8. Okay, yeah, So we can also verify that when y equals 8, the period is equal to 2, the corresponding d prime is 3. And then using this message, you will also get this same original message, which is equal to m. Okay, so that's it. This completes our Shor's algorithm series, starting from 1 up to 7. And okay, so Shor's algorithm is not an easy algorithm. Okay, otherwise, if it was easy, then all of us should have figured it out, right? But it's not easy, and so I would suggest that you go back again if you don't understand. If you still have some questions, okay, you ask me, or you can go back to the to the um, to the recordings. So and then you try to get a pencil and paper, yeah, do the computations yourself, okay, and then hopefully you will be able to understand Shor's algorithm. Okay, so this is one of the most important algorithms in quantum computing. So which means that if you really want to understand quantum computing, then this is one of those things that you need to understand. Okay, so once you understand this, the other algorithms are also, I mean, I would probably say that you can also understand the rest. Okay, so thank you very much, and I hope to see you next time in one of our lecture series. Okay, thank you and goodbye.